McLain, titled Laboratory Investigations of Energetic Neutral Atom Backscattering from Apollo-Era Lunar Grains. So Jason, whenever you're ready.
Okay, I'm going to present our lab work on the detection of energetic neutral atoms from various solid targets, including Apollo 17 Breccia powder. From now on, I'll probably refer to these energetic neutral atoms as ENAs. So ENA observations are becoming an increasingly valuable tool for understanding magnetospheric dynamics and also the heliosphere, as well as solar wind-driven phenomena such as solar wind-induced hydroxylation and atmosphere erosion. In addition, these lab data can help interpret the spacecraft data and in general help us understand the fate of the solar wind hydrogen. The main motivation for this for the study was the observations made by Weiser et al., and I have his figures from his paper here, where they detected extremely high reflection of the solar wind protons from the lunar surface. Basically, their yield was between 16 and 20%, and they've refined this sum with additional analysis, and as well as the IBEX measurements, where the higher energy energetic neutrals were around 10%, and for the lower energies up to almost 17% here. We're able to measure these ENAs in our lab via a UHV chamber, in which we use a differentially pumped mass filter ion source, and we can use this to send pulses of ions onto the sample, and the resulting ENAs are then detected via time of flight. Our Apollo sample was a vesicular breccia, and you can see it here. Let's see if I have the cursor working. Let's see. Yeah. So you can see here, this sample was taken from the rim of Mare Serenitatis, and thanks to a few brave men during an Apollo mission, was brought back for us to analyze. Here's the geometry of our setup here. We can actually vary the incident angle and the scattering angle to produce plots where we can look at the energy distribution. I don't know how that got flipped over upside down, but basically we can make plots like this to determine the angle distribution. And from these plots, we can determine what the yield is. Here you can see we held the incident beam at 90 degrees and varied the scattering angle, and where 80 here would be the directly backscattered energetic neutrals, and 90 would be ones that are scattering horizontal to the sample. It's clear from this plot here that the distribution is a result of the surface morphology as well as porosity. And for the Apollo 17 sample, here you can see the shadowing and the roughness of the sample actually sort of evens out the angular distribution. From these data, we can then, these are upside down as well, but from these data we can then look at this distribution and actually determine what the yield is in the laboratory and compare it to what the observations are. Here, I just wanted to point out that, that neutralization occurs before reflection, and this reflection is a multiple collision process. This distribution here is determined by assuming that the integrated angular distribution is symmetric, which holds true for the very rough surface of the Apollo dust. And I didn't put error bars here, but our best estimate here for at 1 keV for the Breccia powder is about 16.5%. The reason why there's no error here is even though we have very well defined ion fluence as well as our angular extent and the MCP efficiency for the detection, the integrated angular distribution we're working on improving here. So one interesting thing might point out here, which the box actually ended up being a little bit cut off here, was that the interject neutral backscattering yield went down for the Breccia powder quite substantially, and compared to a quartz sample also went down as well. So these are the plots for the different samples. Because we are doing a time of flight detection, we're able to also get the energy distribution. And what might be intuitive is that the interject neutral atoms are dependent upon the ion energy, where if you increase the incoming proton energy, the energy of the neutral also increases. But maybe not so intuitive is that as you increase the scattering angle, essentially becoming more directly backscattered, the energy also increases here. This plot here has I've separated the two different scattering angles for the for measurements at 2 keV, which is in the black circles, and 1 keV, which is the gray squares here, and you can see that the energy distribution is dependent both upon energy and the scattering angle. One of the questions we had then was whether well, excuse me, this next plot here, this was for the first plot was for platinum, but for the Apollo sample, this same trend holds true, and you can see here that the distribution is dependent on both the angle and the energy. These energy distributions are very consistent with what we saw with what Visor published, and while we have a very monotonic energy of incoming ions, we still have an increase here at the lower energies due to the lower efficiency for our detector at these energies. One of the questions we had was whether or not the surface could be, the interject neutrals could be used to interrogate the surface. And if we normalize our three different samples, we can see here that for the 1 keV and the 2 keV, that the energy distribution for the ENAs are very consistent. And maybe for the platinum, there's a slight shift to higher energies for the 2 keV incoming protons, but basically the distribution is the same. And this tells us a good bit about the mechanism that's involved here and how this process is a multiple collision process. So in conclusion, our lab measurements do corroborate the recent observations for the high reflection the solar wind protons, and these backscattering yields are important parameters when considering the lunar, the volatile content and the solar wind-induced hydroxylation. And in the future, we'd like to extend these measurements to other solar wind ions, such as helium-2+. And from these data, we can produce a distribution function to help with the observations. So, thank you.
So we do have a question. TRIM shows
Sure.
backscattering yields of 10 to 20%, as I showed this morning. Why is the reflection in the papers you mentioned at the beginning considered extraordinary?
Yeah, sure. So TRIM it does very well for very, very high energy interactions with solid targets, but it begins to break down for the lower energy once you get to KeV and lower. So.
Okay. And quick question, are you planning to run these types of experiments with other lunar samples from different geologic terrains and such? We would like to, certainly, yes. Okay. If there are any additional questions,